Sathyabama Institute of Science and Technology.
A very good morning. This is Dr. Priya Shirley Muller from the Department of Mathematics, Sathyabama Institute of Science and Technology. Today I am here to talk about discrete mathematics and its applications. So we all know discrete mathematics is the backbone of both mathematics and computer science. Now it is the study of mathematical structures that are countable or otherwise distinct and separable. And if you talk about discrete the structures, they are the combinations, graphs and logical statements. So the logic and Boolean algebra, they form the base of discrete mathematics. So let's begin with that. Let's look at the applications of logic and Boolean algebra. This was actually developed by the English mathematician George Boole in between 1815 and 1864. And this is basically an algebra of logic, two values, true and false. And logical operators are used to perform the logical operations in digital computers. Now, there are three fundamental logical operators. They are the AND, OR, and NOT operators. Now, AND is also called as conjunction, NOT is also called negation, and OR is also called disjunction. Now, we all know what a truth table is, right? Truth table consists of all possible combinations that a Boolean expression can possibly take. So, if the Boolean expression has n variables, then you will find 2 power n combinations in the truth table. Now, there are only two possible truth values that you can have, either true or false. Now, true is usually represented as 1 and false is represented as 0. Now, let's look at what is a gate and what is a circuit. Now, gate is basically a device that performs a basic operation on electrical signals or computers. Now, gates together, they can perform complicated tasks, which then becomes a circuit. Now, Boolean algebra is both applied in computers and electrical signals, electronic circuits. Now, these circuits perform Boolean operations and are called logic circuits or logic gates. Now, as we discussed earlier, the three basic logic gates are the AND gate, the OR gate, and the NOT gate. So, let's look at each gate separately and its applications. Now, the AND gate operates on two or more input signals to produce one output signal. Okay, and it produces a high output of 1 only if all its input signals are 1. So, only if all its input signals are high, only then you get a high output. This is how AND operator behaves. So, here you have the truth table wherein you see that it produces 1 only if both the inputs are 1. Otherwise, it returns 0. Okay? And here you have the symbol that is used to represent an AND gate. Now, let's look at the application of AND gate. Now, we all know the burglar alarm, right? How does it work? Supposing you're leaving the house, then you set the alarm switch on. And when the burglar gets into your house, he sets the person sensor on. And tada, that's how the alarm bell rings. So, this is a direct application of AND gate. And you have a lot of other applications that you can see in your everyday life. Like for instance, if you take the microwave, it will start only if both the start button is pressed and the door switch is closed. Similarly, if you take the electronic doors that you see in the malls, how does it open? Only if it detects a person and if the switch is set to unlock. That's when the electronic doors open. So these are all applications of AND gate. And I'm sure you can think of a lot more. Next up, we have the OR gate. Now, the OR gate is very similar to the AND gate. It also acts on two or more input signals to produce one output signal, but it returns a high output of 1 even if one of its inputs is high. Okay? So, that's how it works. Let's have a look at the truth table. See, it returns 1 even if one of its input signals is 1, and it returns 0 only when both the inputs are 0. So, that's how it works, the OR gate. And this is how an OR gate looks like. The symbol that is used to represent an OR gate is this. An application of OR gate will be a simple doorbell that we have at our homes. Okay? So, when would you expect your doorbell to ring? Even if someone either presses the front doorbell switch or someone presses the back doorbell switch, right? You would expect your doorbell to ring. So that's an application of the OR gate. Now, the NOT gate is very different from the AND and the OR in the sense it only acts on one input signal to produce one output signal, okay? And also, it returns a high output if the input is low and vice versa. Now, it is also called an inverter, all right? So, this is how it works. This is the truth table for the NOT operator or the negation operator, and this is how it looks. The symbol that is used to represent a NOT operator is this, a triangle followed by a round. So this is the application of NOT gate, maybe not in our countries, but it's very, very common in outside countries where the place is really cold. You have something called the central heating system, right? So when the temperature goes below 20 degrees, the central system, heating system is switched on. Similarly, when the temperature goes above 20 degrees, then the central heating system is switched off. So that's a direct application of the NOT gate. So we also have the XOR gate, which is exclusive OR, which is, as you can see from the truth table, this is the truth table for XOR gate. And then we have the symbol that is used for XOR gate. We also have the NAND gate, which is basically not of AND. You know how AND gate behaves. This is not of AND. So that's the truth table for you. And this is the symbol that is used to represent the NAND gate. And then we have the NOR gate. NOR gate is not of OR. So you know how OR gate behaves. This is simply not of that. And that's the truth table. And this is the symbol used. So we also have gates with more inputs. So we also have a 3-input gate. Supposing you have 3 input signals, then obviously how many combinations can you have in the truth table? 2 power 3, which is 8 combinations. So that's the truth table for you, where you have 3 input signals for an AND gate. So this is A and B and C, and this is how you represent using the symbol. So this is a circuit. Okay, so as we discussed earlier, gates together can perform complicated tasks, which becomes a circuit. So the output of one gate is used as the input of another, and that's how a circuit is formed. So if you look at this is AB or AC. It's A and B or A and C. That's the circuit which represents this Boolean expression, A and B or A and C. Okay, and for and if you look at this, this is the truth table for AB plus AC. So again, you have these 8 rows because you have 3 different input variables. So you have 8 combinations, and this is the circuit, and this is the truth table for the circuit AB plus AC. This is the circuit which represents A and B or C. Okay, so this is the circuit, and that's the truth table for the circuit. So if you look at this truth table, does it ring a bell or does it seem familiar to you, this truth table? It's exactly the same that we saw in the earlier slide for A or B and A or C. So you actually see that, 2 expressions, 2 different Boolean expressions which look so different can have the same truth table. And that is how the mathematical principles are developed, When 2 expressions have the same truth table, they are actually said to be equivalent expressions. And this particular law, A into B plus C, is the same as A into B plus AC. Do you all know which law I am talking about? Yes, it's the distributive law. Okay, so you can, these principles actually allow us to help design circuits, 2 circuits which are equivalent, which have the same output. Yes, can be actually formed. So now we come to the end of part 1, wherein we've seen the applications of discrete mathematics in logic and Boolean algebra. And in the forthcoming episode, which is part 2, we will see the application of discrete mathematics in graph theory. So looking forward to meet you there. Thank you.